Myself, Anuj, and I will be presenting directional label diffusion model for learning from noisy labels. The venue is CVPR 2025. So the noisy label is a quite a common problem. It is found in webly supervised data, meaning data obtained from the web, and weakly partially supervised data sets and crowdsourced data sets. The image here shows images of cat, and the one with the orange border is image of a dog mislabeled as a cat. The impact is that it misguides training and evaluation, creating a persistent, clean, noisy accuracy gap. These are the typical noisy benchmarks. Traditional approaches involve robust losses, sample selection, weighting, regularization, for etc. The limitation is that it lacks an explicit mechanism to encode noise knowledge, and the generative perspective, which the paper exploits, is that it models labels as diffusion variables conditioned on visual features. This is different from typical T2I, where text is the condition to generate an image. Here, image is conditioned to generate noisy labels. So this is the diagram. This will be explained in the next slides. So related works are learning with noisy labels. Like I said earlier, robust loss includes mean absolute error, generalized cross entropy, sample selection, example co-teaching, co-divide, and other approaches. Generative diffusion view for labels, they treat labels as continuous variables and denoise with image features as the condition. And directional label diffusion, it extends diffusion with a directional prior that encodes label noise statistics explicitly. Then the method they use is directional label diffusion. So it decouples the diffusion process into two steps, that's random diffusion and directional diffusion. Both are conditioned on the image features. So in the figure we can see we start with y0, which is a label, and the forward process for the random diffusion, it involves adding noise and going to an epsilon, which is sampled from the standard normal distribution. This is not a label distribution anymore. It has negative and positive values. This is not a label distribution. It's just random noise. Whereas in case of directional diffusion, in the forward process, we keep on adding noise and go to a noisy label distribution. This is a noise label distribution. So at time step capital T, we add y small n, which is obtained from directional diffusion, and epsilon, which is obtained from random diffusion. So this was the forward process. In the backward process, we go from epsilon and yn to y0. It is conditioned on the input image. So this is the typical workflow. In the forward process, this is the notation. Y0 is the pre-corrected label. Yn is the directed noise distribution that we want to achieve, noisy label distribution. Yd can be understood as the difference between the Yn, that's the noisy label distribution, and Y0, that's the starting distribution. Epsilon is a sample from a standard normal distribution. Alpha t and beta t are coefficients for the forward distribution process. It's greater than equal to 0 and less than 1. So as epsilon is sampled from a standard normal distribution, multiplying beta t would lead the variance to be beta square t. And as it's zero mean, for yt would belong to the distribution of yt minus 1 plus alpha t yd, that would be the mean, and beta square t would be the variance. So this is what I am talking about, the forward Markov step. Yt conditioned on yt minus 1, yd and x, it comes from this normal distribution. The closed form to go from 0 to time step small t is y0 plus alpha bar small t yd plus by beta bar t epsilon. So alpha bar t is associated with the uh, d is yn minus y0, and epsilon is the random noise that we sampled. Alpha bar t is summation of alpha from step 1 to small t. Beta bar t is the square root of sum of squares from step 1 to step t. The constraint that we have added is that alpha bar capital T and beta bar capital T should be 1. Uh, think of substituting capital T here, so we would get y0 plus alpha bar capital T yd plus beta bar capital T epsilon. As these are 1, it gets simplified to this, and substituting yd as yn minus y0, we get yn plus epsilon, which is what we showed in the figure. So these are certain example schedules which follow the constraint. And in the reverse diffusion process, we start from y0 and t. and t we sample a step, and y d and epsilon are y d is y1 minus y0, epsilon is something that we sample. We have these, and we perform the forward diffusion step and go to yt, which is this step. And we after getting yt we go for the reverse diffusion process, where it is concatenated with the embedding for the input obtained from an external feature encoder. And we also considered the embedding for t, and this is the conditioning for from the image that we were talking about, and we estimate yd theta 1 and epsilon theta 2. And yd theta 1 is predicted, this is the loss function for predicting yd theta 1, and this is the loss function for epsilon theta 2. Why it is predicted in reverse diffusion is can be understood that once we have yd and epsilon, we can subtract it from yt and go to yt minus 1. So this was for the reverse diffusion process. And post the reverse diffusion process, I'll be talking about pre-correction and the directional label diffusion. So prior to directional diffusion, which we already mentioned, there is a pre-correction step from which we obtain the y0 and yn that we have been using in the diffusion equations. So this is the pre-correction step, the stage one. And given an input image and label y tilde, we obtain two augmentations for the image. One is a weak augmentation, one is a strong augmentation, given by xwy tilde and xsy tilde. And we pass the image to a external feature extractor. And the goal is to classify the inputs into three sets: clean set, noisy set, and hard set. And this is how we will obtain y0 and yn for each of the images. And this is the entire directional label diffusion process, which was discussed earlier. So to get y0 and yn, let's say, firstly we have to partition the images into these sets. How this is done is we have the weakly augmented image and strongly augmented image. We take the features for those images, passing it through a feature extractor, and applying certain distance thresholds, we can partition the inputs into these three sets. Now, if the model thinks that our input is from the clean set, it would mean that y0, the original starting point, is clean, so we can use it as it is, y tilde, and yn, which is the noisy label that we wanted, it is considered as 0 as the starting label, as the input belongs to the clean set. If it's clean, then the module assumes that its starting point is not noisy, so we don't need to have any noisy label distribution that we want to go to in the directional diffusion part. If it is from the noisy data set, we obtain PWS, that is the average of the logits of the weakly augmented image plus the strongly augmented image. Taking argmax gives the class for which the logit value is highest, and one hot is just 0, 0, 1 at the classes index, and rest all zeros. So, and the yn would be y tilde as the origin, as x belongs to a noisy set. It means that the original starting label for the image was thought to be noisy by the model. So that is the noisy label that we want to go to in the directional diffusion process. And if the input belongs to the hard set, then we use PWS, which is the average, and this is how we obtained yn, which is the difference between the distributions. And these equations hold from earlier. This is a toy example given four classes: cat, dog, car, and frog. Suppose your sample belongs to the clean set and it's the cat class. So even after pre-correction, as the model thinks it belongs to the clean set, y0 would be same as the starting point y tilde, and yn here is 0 as we don't want any directional diffusion. We just want random noise. If it is noisy, and the original label is given as cat, but PWS predicts it to be a car, then y0 would be this, and y capital T would be y noisy, the vector we want to get after the directional diffusion, which was the starting vector y tilde plus random noise. And if it's hard, then PWS we take an average of PWS, which is 0.45 plus 0.55 is 1 divided by 2 is zero point 0.5. And this is how we get this vector. And yt is the difference between the PW and PS. So this was a toy example. The algorithm is we have a training set x and y tilde, feature extractor f external, and two network parameters theta 1 and theta 2. One was for yd1 as stated earlier, and one is for epsilon theta 2. Output is theta 1 and theta 2. Given augmented features for strongly and weakly augmented images, we pass them through feature extractor f external. We obtain dw and ds, and we calculate k nearest label distributions, that is pw and psd logit distributions, and we partition the samples into these three sets from which we obtain y0 and yn. And while training has not converged, we sample the data from the weakly and strongly augmented data. A time slice t, which is characteristic of any ddpm, we for the forward process we just take a small time step t, and we have the equation to go from y0 to yt. We estimate y0 and yn using the preconditioning, uh, like stated earlier. This is the preconditioning, and the losses which were explained over here, these are the loss terms. So, and we take gradient descent on those losses to update the network parameters. The experimental setup includes the feature extractor, which is pre-trained models which are pre-trained to avoid any label noise bias. Those include ResNet34, SimCLR, and VITL14. And the losses, as stated earlier, stay the same. The data sets is CFAR 1000. This is a synthetic noise. And these are real world noisy data sets. And inference is accelerated like DDIM, like generation in approximately 5 steps without accuracy loss at class level. So these class-wise accuracies, this is synthetic noise that is added to CFAR 10 and CFAR 100, as these are not actually noisy data sets, and this is instance-based noise. What that means is that the probability of misclassifying a cat as a dog is higher as compared to misclassifying a cat as an airplane. Like, the synthetic noise that they add also depends on class semantics. So these are the accuracies for the noisy datasets. In both CFAR 10, 100 and noisy datasets, we can see that DLD outperforms the existing methods. So, like I said, it outperforms. And it also depends on the external feature extractor. VITL14, it yields the best overall accuracy. And on real world noisy datasets, it also performs well. That indicates strong robustness beyond the synthetic noise. And the so essentially, to summarize, DLD, it proposes decouples diffusion into directional and random channels, and the pre-correction, it estimates y0 and yn, which is the starting point, and yn was the directional diffusion via which we wanted to obtain the noisy label distribution in the forward process. So these are this is the training process. There are two predictors and L2 losses, and it is empirically strong on CFAR. This is instance-based noise and the real-world data sets. Future scope includes to integrate both discriminative and generative paradigms and explore richer feature conditioning and analyze theoretical guarantees under diverse noise models. Like, this was just instance based, there could be mixed noise and other types of noise as well, and try with different solvers, diffusion solvers, to see how the performance gets affected. Thank you.